Welcome. So we are discussing about AVL trees. AVL trees are self-balancing binary trees. That is, after performing insertion, if the tree got unbalanced, then we perform certain rotations to ensure that once again the tree gets balanced. That is, once insertion was done, then immediately you have to calculate the balance factor for every node. The accepted balance factors are 0, -1 and 1. As long as the balance factors for every node is either 0 or -1 or 1, we call the tree as a balanced tree. But for if any of the node, for any of the node, if the balance factor becomes greater than 1 or less than -1, then we say that the tree is unbalanced. So in that case, we have to perform rotations. So we have discussed an example case in the last lecture. So these are the four possible cases for unbalancing and again to rebalance, right? So LL means the new node Y is inserted in the left subtree of the left subtree of A. A is the one which got unbalanced. Then you have to perform a right rotation. LR means the new node is inserted in the right subtree of the left subtree of A. A is the one which got unbalanced. Then we have to perform two rotations, a left and a right rotation. Okay. RR is the new node is inserted in the right subtree of the right subtree of A. A is the one which got unbalanced. In that case, you have to perform a left rotation. Okay. For LL, one right rotation. For RR, one left rotation. Okay. RL means the new node is inserted in the left subtree of the right subtree of A, which got imbalanced. In that case, we have to perform a right rotation and a left rotation. So we will try to generalize these rotations. So in a given tree, how it will be done, right? So here the left side, whatever the first diagram, whatever you are seeing, this is a balanced tree. This is actually, it's a balanced tree, right? There is a node A, to the left there is a node B, and this is the left subtree of B. Okay, there may be many nodes, we are not showing all those things, and this is the right subtree of B, and this is the right subtree of A. Okay, right? So let us assume the height of the right subtree of A is h. Okay, height of right subtree of A is h, and the height of the entire tree is h plus 2. Okay, entire tree is h plus 2. So actually the tree is a balanced one, right? Of course the height of B is slightly lesser, but the balance factor, if you see, it will be 1. So here this is a balance factor. The balance factor of A is 1, balance factor for B is 0, because both its left child is of equal height. Okay, whereas if you see the balance factor of B, it is slightly more than A. Okay, right? Fine. So the height of left subtree of A is h plus 2. Okay, h plus 2, and the height of the right subtree of A is h plus 1. So this is h. So if you include this also, it becomes h plus 1. It becomes h plus 1. Okay. So h plus 2 minus h plus 1 is what? It is 1, right? Okay. So this is a balanced tree. But here an insertion is done. Let us assume that in this balanced tree, you are performing an insertion here. That is, one more node is added to the left subtree of B. So this is a new insertion happened. And because of this, now the tree got unbalanced. Where the tree got unbalanced? Tree got unbalanced in node A. Okay. So what kind of rotation now we have to do? So the new node is inserted in the left subtree of A. Okay. The new node is inserted in the left subtree of B, which is the left subtree of A. Okay. So this, now you have to perform one right rotation on A. You have to perform one right rotation on A. So when you perform a right rotation on A, what will happen? this B will come up. Here you will get B. Okay, here you will get B, and this A will go down. A will go down. A will go down, and this AR will be as usual as the right child of A. But when B comes up, where this BR will go? BR is greater than B, so it is less than A. So it will become the left child of A. It will become the left child of A. Okay. So this will be the result of this rotation. So you can see here, after this rotation, B becomes the root of the tree. A goes down, but the right subtree of B, previously whatever the right subtree of B, that has now become the left subtree of A. Okay. So this would be the result of this particular rotation. Fine. So similarly, next let us see how we rebalance for RR case, right rotation. Okay. So again this is the this is the balanced tree. Here the balance factor for A is -1, B is 0, right? But here in the right of B, one more node is added. When you do this insertion, the tree becomes imbalanced. Okay, so that is the balance factor of A becomes -2. So now the tree is unbalanced. So now you have to perform some rotation. But what type of unbalance it is? It is the unbalance happened in the right subtree of A. Okay, that is it is in the right subtree of B, which is to the right of A, right? So that is unbalanced occur on the node which is the right subtree of some other node, and that some other node is the right subtree of A. So now you have to perform a left rotation on A. Okay, when you perform a left rotation on A will come down. If A comes down, then B will go up. Okay, so this will become B. This will become B. Okay, and A will come somewhere here. A will come somewhere here, and AL will be the left subtree of A as usual. When B comes up, where will this BL will go? BL is less than B. BL is less than B, but actually it is greater than A. So it will become the right of A. It will become the right subtree of A. Okay, it will become the right subtree of A, and this B will go up. Right? So this is the change that you will get. So when you do this rotation, this is what happens. B goes up. So B comes here, and to the B is right as usual. It is BR. Okay, and A goes down. But previously, whatever the left child of B, that will become the right child of A. Okay. So now actually this is a balanced tree. The resultant tree is a balanced tree. Right? Okay. So next let us see the case for LR. So LR will be discussing under three cases. First let us assume the tree is very small, something like this. There are only two nodes, A and B. Okay. So here if you see the balance factor of A is 1, for B it is 0. Okay? Because height of left child of A is 1, right child is 0, so it is 1, this is 0. Okay. Now you are performing one insertion C, which is to the right of B. Okay. Now actually A got imbalanced. Okay. So here there is a +2 comes, so A is imbalanced. But what type of imbalance it is? This imbalance happened to the right subtree of the left subtree of A. It has happened in the right subtree. So first it has happened in the right subtree of the left subtree of A. So it is LR imbalance. Okay. So okay. Right. So it is coming left and right. So it is LR. Okay. In this way, if you see right subtree of B, which is the left subtree of A. Okay. From the node which you have inserted, from that direction, if you see, it is the it is in the right subtree of some node, which is the left subtree of the node on which the the imbalance created. Okay, so it is L or imbalance. Okay, so now actually you have to perform two rotations. You have to perform a left rotation and a right rotation. So first we will perform where we should perform left rotation. You have to perform left rotation on where the direction is changing. So the imbalance was created in A. Okay, so if you come down to the, so from A you try to reach C. When you are trying to reach C from A, first you have to reach B. Okay, so that is to the left of A, and then but you have to go to the right of B. So here the direction is changing from left to right. So the node on which the direction is changing, on that node you have to perform a left rotation and then a right rotation. Okay, so when you perform left rotation, what will happen? This B will come here, but this C will go here. Okay, so after performing the left rotation, the tree will be something like this. After performing the left rotation alone, okay, the tree will be, there is no change in A. A is as usual here, okay, but C will come here. C will come here and B will go down, and B will go down. Okay, B will go down. Again, this is actually an imbalanced tree. So for B the balance factor is 0, for C the balance factor is 1, for A the balance factor is 2. Okay, now this is something like an LL. Okay, now it is again in imbalanced. Okay, so now once again you do a right rotation. Once again you do a right rotation on A. Okay, so when you perform a right rotation, what will happen? A will come down. Okay, so this is the result after performing the right rotation. This is the resultant tree you got. Okay, so now when you perform the right rotation, A will come down. Okay, so A comes here, and this is the resultant tree, which is a balanced tree, right? Okay. Now let us discuss another case for left LR rotation. This is case B, right? So here if you see, here this is a balanced tree. Okay, so in this tree you are performing one insertion here, which is to the left of C, Now the tree got imbalanced. Okay, tree got imbalanced. So again you have to check where the imbalance occurs. Imbalance occurred at node A. So if you try to travel from node A to C, first you have to travel to the left of A and then to the right of B. So here the direction is changing. So here first you have to perform a left rotation. So when you perform a left rotation, what will happen? How the tree will transform? First let us see that. So when you perform the left rotation, A is here, there is no change in A. When you perform the left rotation, C will go up and A will go down. Okay, so C will become the root of that particular subtree. Okay, and B will come down. Okay, B will come down. There is no change in the left child of B. B's left child is BL as usual. B's left child is BL. Okay, now C has gone up. So where this CL will go? CL is less than C but is greater than B. So it will become as the right child of B. CL will become the right child of B. Okay, so here will be CL. Okay, and the new node is also inserted in CL, and CL will be now the right child of B. Okay, and the right child of C, that will be remain as it is. Okay, right child of C is what? CR. Okay, there is no change in that. Right subtree. Right subtree of C is CR. So that will be same as it is. This is the left subtree of C. Now it has become the right subtree of B. Okay, and to the right of A you will have as usual AR. To the right of A you have as usual the right subtree of AR. Okay, so now we have performed one rotation. Okay, right? So but again if you see, still this tree is not balanced one. So now we have performed only left rotation. So once again you have to perform a right rotation. Right rotation. Okay, so now when you perform right rotation, A will come down. Okay, C will become the root. So this is the resultant tree. C will become the root of the tree. A will come down. Okay, A will come down. But when A comes down, or when C becomes the root, where this CR will go? CR will become the left child of A. CR will become the left child of A. Okay, right? So this is how the CR will become the left child of A, and there is no other changes. Okay, B will become the, C will become the root, and C's left child is B, and B's left child is BL, B's right child is CL, right? So this is how the second case of rotation happens, okay, in LR, right? Okay, so there is another case. So in the previous case, the new node was inserted to the left of C. Here we are inserting new node to the right of C. That's the only difference. Okay. So here the original imbalance tree is not shown. So here, after performing this insertion, the tree got unbalanced. Okay, the tree got unbalanced. Now you have to balance it. So the insertion happened here. So if you travel from the root to this node, it will be first go left and then go right. So here the direction is changing. So it is left right. Okay, so here you have to perform a rotation. First you have to perform a left rotation here. Okay, so when you perform a left rotation here, okay, when you perform a left rotation here, what will happen in the sense, B will go down and C will become the root of the tree. Okay, so root of this subtree, root of this particular subtree. So after performing the left rotation, so it will be something like this. After performing the left rotation, A will be the root, there is no change in the root of the tree. Okay, but C will become the root of the left subtree. C will become the root of the left subtree. B will go down. B will go down, and B's left subtree will be BL. B's left subtree will be BL. Okay, B's left subtree will be BL. Right? Okay, but when C goes up, where the CL will go? CL is less than C, but is greater than B. So CL will become the right subtree of B. CL will become the right subtree of B. Okay, and CR will remain as usual as the right subtree of C. CR will remain as usual as the right subtree of C. Okay, and AR will remain as usual as the right subtree of A. AR will remain as usual as the right subtree of A. Okay, so this is the resultant tree. What you will get is, okay, this is the resultant tree what you will get. Okay, but now again if you see, it will be imbalanced at A. Okay, so again the balance factor of A, if you check, it will be 2. Okay, so once again what you have to do is, you have to perform one more rotation, that is perform another right rotation on A. So when you perform right rotation on A will go down, C will become the root of 3, and then where this CR will go, CR will become the left child of A. So this will be the resultant tree that you will be getting. Okay, so after performing left rotation, this is what you will get. Then after performing right rotation, this is what you will get. Okay, right? So similarly, you can draw the tree for oral. Oral also you can draw like these 3 cases. Okay, I am leaving that as an assignment. Okay, for example, say A is here. Okay, A is here. B is here. Okay, A is B here. B is here. Right? Okay, now if C is added here, so this tree is balanced tree, right? Now if C is added here, then what will happen? The balance factor of C is 0. The balance factor of B is 1 minus 0, it is 1. The balance factor of A is 0 minus 2, so it is minus 2. Okay, so now if you see, if you start from A, it is left and right. Okay, so here actually, yeah, what you have to do, you have to perform a this is RL. Okay, this is RL. Okay, right and left. Okay, so here you have to perform a right rotation. Here you have to perform a right rotation. Okay, so when you perform a right rotation, what will happen? When you perform the right rotation, B will come down. B will come down, and C will go up. Okay, so that means the tree will become something like this: A, C, and B. A, C, and B. Okay, so again now if you see, the balance factor of B is 0, balance factor of C is -1, okay, 0 minus 1 is -1, balance factor of 2 A is -2, okay. Now once again you perform a left rotation, okay. Now if you perform the left rotation, what will happen? Left rotation on A will become the left child of C, okay. So as a result what you will get is C, as a result what you will get is C, A and B, okay, C, A and B, okay. So this is a balanced tree, okay, right. So this is the case 1 for RL, okay. Similarly you can work out for case 2 and case C, okay. So in case 2 what you have to do? In case 2 what you have to do is this subtree part you have to move to A, okay, right. So the original tree you have to take something like this, original tree you have to take something like this, A, okay. Leave the left child of A as AL, one big thing, we are not bothered about that, okay, because now we are talking about RL rotation, right, left, okay. So this we will call it as AL, this will be called as AL, and the right child of A is say B, okay, right. So say B is right is BR, so B is right is BR, okay, B is right is BR, and to the B's left you have C, to B's left you have C, okay, C, and then you have here CL and CR, okay, here you have CL and here you have CR, okay. So this you can consider as the initial balanced tree, okay. And then two cases you can discuss, okay. One is right left, one is you perform an insertion at here, okay, that is in CL you are performing an insertion, right. In that case how you will perform the right right left rotation, and the second case you can take as performing rotation in CR part, okay. So in the first case insertion will be done here, in case B, okay, and then how will you perform right left rotation, okay, right. So and in the second case you can assume insertion is done here, then how will you perform right left rotation, are you getting, okay, fine, okay. So in the first case, if I assume that the insertion is done here, then you have to rotate B to the right, okay. When you rotate B to the right, what happens? C will become the root and CR will become the left of B, okay, right, okay. In the second case, when you perform insertion in CR, so again you have to perform right rotation. Again, when you perform right rotation, so what will happen? Again, B will go down and CR will become the right of B, left of B, okay. So that you have to work out, right. You just figure that out how it happens, okay, fine, right, okay. So after rebalancing, actually you need not check whether the tree is balanced or not, because once you do rebalancing, automatically it will become balanced, okay. So why we are going for AVL tree, that you know, because insertion can be done at the speed of order of log n, whereas with normal binary search it will be of order of n in the worst case scenario, okay. And the researchers has shown that random insertion requires no rebalancing generally, okay, and a rebalancing rotation of type LL and RR, and this is the probability of rebalancing rotation of type LL or RR does not generally, and a rebalancing rotation of type LL and RR with probabilities. So these are the probabilities of occurrence of these type of rebalancing, okay. For LL and RR, the probability of occurrence is 0.5349, okay, and for LR it is 0.2327, and for RL it is 0.2324, okay. That means more rotations will be either LL or RR with a single rotation, okay, and the probability of LR and RL is almost equal, okay. So you can say that LL and RR occurs 50% of the time when you are doing rotation, and remaining time it is for either LR or RR, or RL, which each occupies close to 25%. Right? So these are some of the comparisons of various what you call algorithms or various approaches. So here we are comparing three, three, three data structures. One is the sequential list, okay, and then the linked list, and then the AVL tree. Sequential list is nothing but arrays, okay. Sequential list is nothing but arrays, right? And linked list, you know, we have discussed, right? And this is AVL tree, okay. So searching an item X in a sequential list. Okay, so here sequential list in the sense it is array, but also we assume that the array contains element in ascending order. We also assume that the array contains element in ascending order. If there are some 10 elements, then it is something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is always in the ascending order. Okay, it is never in the any other order. Okay, that assumption is done. In that case, if you want to search an item X from the sequential list, given that the list is in ascending order, it will take order of log n times. Why? Say for example, from this list I want to search where is 7. Okay, so what I will do is I have to first take the mid of the array. The array contains 7 elements. Okay, so what is the mid? Mid is 7 by 2, which is 3.5. 7 by 2 is 3.5. 3.5 means I can either go for 3 or 4. Okay, so check the third element. What is that? Okay, check, or we'll take upper bound. Okay, check the fourth element. What is that? It is 4. What I want to search? 7. So is it greater than 4 or less than 4? It's greater than 4. So it means it means that it is in the right side of the array, not in the left side of the array. So the right side contains how many elements? Again 3 elements. Okay, right side contains 3 elements. If you divide 3 by 2, what you will get? 3 by 2 is 1.5. Okay, 1.5. And previously already we are in the fourth location. So 4 plus 1.5 is 6.5. Okay, 6.5 means you go and look 6.5. If you take the upper end, it is the 7th location. Check there. What is this? Is it 7? Yes. So in just 2 iterations, we have identified the number, right? So this is similar to binary search. In binary search, in binary search tree, we are doing the same thing on the tree, right? So here the search, the time complexity for search is order of log n. So this type of searching a list is called as binary search. Later we will learn this. So this is called as binary search. It is possible only if the list is arranged in ascending order. Okay. Whereas in the linked list, it will take order of n times in the worst case scenario if the number is in the last location. Okay. In AVL tree, it will always take order of log n times because AVL tree is a self-balancing binary tree. Okay. Fine. To search for a kth item in the array. So if the array is already in the ascending order, then kth item you can just refer as A of k. Kth item. If I want to identify the 5th element, then it is just A of 5. Or in C it is A of 4. Okay. So it is a constant time. It is of constant time, order of 1 times. That's it. Okay. So that it is order of 1. Okay. Similarly, in linked list, but it will take order of k. It depends on the location of k. Order of k. In AVL tree, it is order of log n. Okay. And deleting an item X in sequential list, it depends on the item where it is. Okay. It is order of n times. Okay. In linked list, it is order of 1 times. But here, actually, we are assuming that the linked list is a doubly linked list and the position of X is known. That is, if you have a pointer to X, then you can easily delete it. Then in that case, it takes a constant time. But in AVL tree, it takes order of log n times only. To delete a kth item in a sequential list, it is order of n minus k. In the sequential list, if the size of the array is 7, and if you want to delete a third item, okay, then after deleting third item, you have to move all the remaining items to the previous locations. Like that, how many moves you have to make? You have to make n minus k moves. Okay, if you want to move the third, delete the third item, then 7 minus 3 is what? 4. So 4 movements you have to do. 4 should be moved, 5 should be 6 and 7. So n minus k. Whereas for linked list it is order of k. Okay, because you can identify the element and just delete it. So how much time you take to identify the k, that is the core thing. But in AVL tree it is order of log n. To insert an item x, the sequential list it is order of n times. Whereas for linked list it is order of 1 times. Okay, as considering that the position of insertion is known, that is at which position you want to insert, you have a pointer for that. Okay. For AVL tree, the insertion is order of log n. Okay. Output in order. If you want the output in particular order, that is in ascending order, all those things, then in sequential list it is order of n, because every element you want to output. In linked list also it is order of n. In AVL tree is also it is order of n, because every item you want to visit and print. So everything should be, every node should be visited. Okay. So if you see here, for most of the cases, other than output in order, the AVL tree's performance is of order of log n. So compared to all these things, all these three data structures, actually AVL tree performs in a better way. So that's what we are discussing here. Okay. Fine. Let us stop this lecture here. Okay. Thank you.